All right, so now we're going to look at the long-run behavior of rational functions. And we're going to start with this example where we have f of x is 3x squared plus 2x minus 1 all over 2x squared plus 1. All right, so we have this rational function. And the first task is just to complete this table. All right, so we're going to put some values in. Now remember that long run behavior has to do with what happens to the function as x gets really, really large in the positive direction, or more and more and more negative, right? In the negative direction. Okay, when we go to the extremes in the long run in both the positive and the negative directions. Okay, so that's what this table is set up to show you. So I'm going to start in the middle because f of 0 is easy to evaluate. I'm just going to put in 0 for x, right? So 3 times 0 is 0, 2 times 0 is 0. Everything goes away except for the constants, -1 on top and 1 on the bottom. So f of 0 is just going to be -1. All right, now the other ones, if I put in -1, now I probably won't. You can go through and put these numbers into your calculator and see what happens. But I'm going to go ahead and just give you the results. When I put in -1, I got 0. When I put in a positive, I got 1.333, right? Because it's going to end up being, what is it? 5 minus. No, wait a minute. So it's going to be right. It's going to be 5 minus 1 all over. So it's just 4 all over 3, right? So 4/3 is 1.333. All right, so then I'm just going to plug in 10, 100, 1,000, and I could keep going. I could put in 10,000, I could put 100,000, I could put in a million, but my table's not that big, so I only had room to go up to 1,000, but you'll get the gist of it when you see what happens. So I put in 10, and I got 1.587, and that's rounded off to 3 decimal places. When I put in 100, I got 1.510. And then when I put in 1,000, I got 1.501. Again, these are all just rounded numbers. But it looks like the value is getting closer and closer to 1.5. And if you put in larger numbers, if you put in a million into x and calculate what it is, you would see that it is truly getting closer to 1.5. All right, so let's go and look at what happens when we go in the negative direction. So if I put in a -10, I got 1.388. When I put in -100, I got 1.490. And then when I put in -1,000, I got 1.499. Okay, that's supposed to be a 4. I'm going to make it look more like a 4. 4.4. Okay. So now you can see when we're going in the negative direction, it also seems to be getting closer and closer and closer to 1.5. It's coming at it from a different direction, though. It's coming up from the bottom, right? It's getting closer from, to 1.5, but it's coming at it from numbers that are less than 1.5. Whereas on the other side, we were coming down, right? We're coming down to 1.5. So let's describe the long run behavior using limit notation. So I have this function f of x, and in order to describe this long run behavior with limit notation, I'm going to look at, first of all, the limit as x goes to positive infinity of f of x. All right, so I'm taking the limit as x approaches a positive infinity of f of x, and it appears to be going to 1.5. Same way with the limit as x goes to negative infinity. Okay. It also looks like it's going to 1.5. Okay, so that's how I would describe the long run behavior using limit notation. You want to look at both what happens when x gets larger and larger and larger in the positive direction, and what happens when x goes farther and farther in the negative direction. Okay, so you want to look at both x going to infinity and x going to negative infinity. Now, this goes beyond what the problem is asking, but it leads us into our next concept. So I'm going to go ahead and just sort of graph what this function looks like given what I know. All right, so I have this function, and I've got this value 1.5. So I'm going to say this is about 1.5. I'm going to say this is the line 1.5. Y equals 1.5, right? Because these f of x values, those are if I say y equals f of x, right? Then this is the line y equals 1.5, right? So that means it's crossing here at 1.5. So let's we know f of 0 was -1. So if that's 1.5, then -1's maybe about here. Okay, so there's a point here at -1. And then at -1, we're at 0. So let's say this is -1 also. We have a point there. Okay, so we can kind of connect those up. And then what's happening here? Now at 1, let's say we're at 1. Now we're at 1.3. So let's see. This would be about where 1 is. So 1.3 would be just below that. And then it goes above 1.5, right? So it goes above 1.5, but then it starts coming down toward 1.5. So that's why I drew in that line y equals 1.5, because it peaks up at some point above that line, but then it kind of goes gradually down toward that line y equals 1.5. Now on the other side, it doesn't appear to be crossing 1.5, but it's approaching 1.5 from the bottom. So it looks something like that. So if I was going to graph it, I would say, okay, that's probably sort of what the graph of this function looks like. So let's take a look at Desmos to verify that. So here I have Desmos open just to verify my what I was thinking the graph would look like, and so you can see here what the graph actually looks like. I've put in the function, the same f of x function that we were just looking at. I also put in this horizontal line y equals 1.5, because that seems to be what's happening. That's the limit as x approaches infinity or negative infinity. So as x gets larger and larger in the positive or the negative direction, it's approaching that line. Okay, so my sketch was pretty good based on the information that I got. So this line has a special name, and it's called a horizontal asymptote. Oops, asymptote. Okay, so so that kind of brings us to our next concept, and so I'm going to just go ahead and look at the next box here, which we're going to use in the next example. But in order to look at the long-run behavior of a polynomial, we really only need to look at the leading terms of the polynomial in the numerator and the polynomial in the denominator. And if you have a situation where those where the limit as x approaches infinity or negative infinity approaches a finite number, then you have a horizontal asymptote. Okay. All right. Well, I will stop here, and I'll meet you in the next video for the next example.